Hello, everyone. Today we are going to talk about a recommendation system design, which is a very interesting topic because it's kind of overlap between machine learning system design and um, like distributed system design, engineering system designs problems. It's good to learn about it. In this system design, we are more focused on like distributed system design aspect of it. However, um, we will point out some topics regarding to machine learning mm, aspects of this question as well. But in order to learn more about it, as you might know, ML system designs are very different. The topics are different, and the focus are different. You need to learn on them separately. Okay, let's get started. Let's talk about functional requirements. System collects server logs and based on users' interest and users' activity, interest comes from activity, right? Like how many times they have liked a product, or what is their comment, and then sentiment analysis or that comment, and then how many times they have ordered that one product, like what is their click rate, what is the conversion rate, all that. Those are activities that a user can do, on internet, on some websites, some, products, or any type of products. Is it a movie? Is it like a product? Then that shows their interest level on that product or that movie. And then recommendation server responsibility is to gather those information and then aggregate them, maybe like inject them into ML models, get the result, and give a set of recommended products to the user. So at the end, after this collection workflow, the main um, functionality is to generate a list of recommended products, movies. Number two, system makes those recommendations available to user in their first page and or let's say their feed, right? And it needs to be um, pushed to their web page without needing to fetch them in order to make it like more performant. And if they need more recommendation, maybe they can scroll in their feed, and then the rest of recommendation can be like a pool. But the most popular recommendation should be pushed into their feeds. System also send advertisement emails and notification to users. Okay, this is an interesting um, functionality as well, to send an advertisement. When we know what they are interested in, we'll send more advertisement, and notification to user. So let's talk about non-functional requirement. System should be reliable. System should handle high activity throughput. By activity, it means click, comments, like, dislike, etc. But the number of these activities are high, handle high activity throughput, real time, and highly scalable. This needs to be real time. When we see the word real time, like in different system, it means a little different. But in our system, in this system, it means the collecting data and generating result should happen in a stream manner. That is a stream processing. Uh, It's not like a batch processing thing. End-to-end latency, a few minutes is acceptable from the time that we gather logs, process them, aggregate them until the time that it's ready to be shown on the user's feed. In the end-to-end latency, few minutes is reasonable. This doesn't need to be real time, but the online part, the part that users fetch their let's say some application, it could be I don't know, like YouTube, it could be Netflix, which is using this recommendation service behind the scene. That piece should be that should have a very low latency because the result recommendation should be ready to be fetched by end user. Low latency for showing result to users. And by low latency maybe less than 100 millisecond. Retention policy, like do we want to keep the data, raw data, it means that activities, or aggregated data. Aggregated data, it means that after we have done all like processing and we have come up to like a suggested list for users, list of recommendation. How do we need to save them, store them, and if so, what is the retention policy? Let's say for raw data, we want to keep them 1 year and then we'll archive them in a like cheaper storage, or we purge them. For aggregated data, we would like to keep them for 5 years. Move to S3 after retention time. Let's talk about the scale of upcoming logs. We wanna focus here is, let's say we have 100K per second logs. Okay, logs are, we will have activity logs at the rate of 100K per second, which is a high throughput for data processing. What will be our choices for storage? For raw data, we will have the size of the data for storage. For raw data, we said we have 100K per second. New data, new log coming. So if you multiply this in 10 to the power of 5, which is a number of seconds in a day, and then multiply it to 365, and which is like a number of days in a year, and then we only want to keep it for 1 year, so it'll come up to 4 terabyte of data. This is 4 terabyte of data for raw data for 1 year. It doesn't seem a big number here for 1 year. Maybe like few database can handle it. But we'll talk about the choice of database. NoSQL databases, they are definitely, they are scalable and they can handle any large amount of data. But here, because we decide to purge the data after 1 year, maybe we can go with one commodity server. Then the other thing is that recommendation data. Recommendation data, let's say the same scale of terabytes of data we need to keep, and the retention time for this is longer, so the scale will be higher, and we need to keep in mind. And because data keeps coming, and that DB definitely needs to be auto scale to handle the volume of data. So this is high level design. As we said, this is going to be at least from the processing pipeline, like processing type pipeline, this is going to be a streaming design, stream processing design. And the reason is that data is not only huge, it's ever coming, and every data needs to be just processed like one time. So whenever these checks are passed, it means that system needs to be, we need to go with a stream processing system design. So we have like activity log servers here. We will have like a producer service or like a front service that is working with a system discovery to pull log servers, maybe in like a batch format to increase throughput. Because we know that small network fetch is going to kill throughput, right? This needs to be handling high throughput. So this can be a pull. The other way is to push, to have push mechanisms so that the log servers push the data to producer service. Then there must be some kind of rate limiting and whitelisting, not to allow for security purposes, not to allow any server to push stuff to producer server. And in the push model, activity servers are buffering the logs, activity logs, like line of logs in a buffer. And then when the buffer size gets to, like, let's say, I don't know, 1 kilobyte, or I don't know, 50 kilobyte or 1 megabyte, then they will push it to producer server. That could be based on the size of the buffer, or it could be based on the some timing intervals. Every 5 seconds they emit log lines to producer service. Then producer service, what it does is that it will serialize these upcoming logs, message, and put a message in a message queue. And this is all because we want it to be to scale well, especially on worker side. Producer server might not be able to handle the processing of this huge amount of data. It's that is why we going with this async design, to put things in message queue, and then we'll have workers that will be working on each message, and like in a streaming fashion. Spark is streaming, yeah, or maybe that is AWS Elastic MapReduce, and then those aggregate data turn the log into more meaningful entries, and store them in like a database to be used by our ML models. We are preparing data for our ML models. We know that ML models, they before we use inferences, we need to normalize data, filter, parse data, create the data in a right format for ML models. This is what we are doing, and we store it here, and then that date then we'll call some inference. We will do ML inference, and we provide that data to ML models, and then the ML models work on top of it, and create recommendation list, and recommendation list can be another data store, a data set with these two data sets can be just key value stores and highly scalable, something like DynamoDB, for example, if we are using cloud to store them. And then from there we will have like a feed service, which will get these recommendation lists and make it available to user through this API gateway, and also they put them in a cache. So here, this is basically a pool model. User is pooling data from feed. So, and feed is reading data from recommendation service. This is pool model, but we, in order to make it low latency, we put it in like kind of elastic cache. In this system design, we are mentioning like the cloud AWS cloud terminologies. Elastic cache, which is scalable also. AWS Lambda feed service, it's serverless and scalable, auto scale, based on the number of requests for this feed. This is a pool model. However, we could also make this like a push model, so that some other service will after we create these recommendations, we like if kind of fan out service which read these recommendations and write directly to cache, make it available for database and cache, make it available for AWS Lambda. Yeah, this is a stream lane, a stream processing lane, and main lane. However, in this design, for reliability purpose, we have added another batch lane as well to make it more fault tolerant. Because let's say if a streaming service doesn't work for any reason, and fails, we want to also store log events, the raw data, in order to be able to recreate recommendations in batch mode from raw data. So that is why this the message queue that we have in this model, after producer put messages in message queue, there is another service which has subscribed to message queue, which is responsible for writing the raw data in some data storage, some like S3 raw logs. We are talking about raw logs. And then this service could be a AWS service like Kinesis Firehouse, read from this queue and write it into S3, and then we have a glue. We have a glue, AWS Glue, which works on this data, puts some kind of schema on top of it, and make it available for Elastic Map Reduce batch job to process this data and to create, let's say, a list of recommendations, okay? And save it in a DynamoDB. Then if we are we want to make it kind of sync with the stream processing, we will have a reconciliation service which at some intervals, maybe at the end of each day, they will compare the result of batch lane and the streaming lane for every single day, and compare and correct the data. The source of truth here should be uh, the batch, especially if there are like some inconsistencies with a streaming line, or we have just created that is a new lane and it is still in testing phase. Then this batch lane comes in handy to make sure that the system is is under, let's say, test, and it's becoming more mature over time. So um, then this is a very uh, I think we already covered a lot of areas still, like machine learning techniques. We just mentioned it here. This is not very, we didn't go to detail, but like the way that we are calling that those inference APIs, and how we basically preparing data. We didn't go to those specifications, because that's out of the scope of this system design. However, keep in mind and get ready for it if they ask more about that area. Deep dive. Number one, push versus pull when we fetch data. Push needs to buffer logs and send based on time or size threshold. In pool, front service should consult with the discovery service, Zookeeper, for example, to have access to a list of log servers. We prefer pool because there is more control in hand of front service, like whitelisting of authorized servers, etc. Push will need load balancer to do rate limiting to avoid DDoS attack. We mentioned all these. Number two, aggregate workers can auto-scale based on metrics such as queue size and resources, CPU memory to scale independently, um, if needed, based on traffic and resources. For low latency of feed service, we cache the most recent generated recommendations. Services and data need to be distributed in multi-zone, even multi-region for high availability on geolocation, and because of geolocation and lower network latency. That is for all distributed system, that should be in place, because we need to make it low latency and geographically distributed. That's why we will need replicas of both data and services in multi-zone and even multi-region. And we'll have like a geo load balancer, or DNS, to route the request to appropriate machines, servers across the network, and also access the data from the closest data center to the user, to the end user. For reliability, we have a batch lane as well as, so that is for reliability. We have a batch lane as well as to aggregate result from raw data and compare with a stream lane result. We can downsample raw data to lower the storage cost. This is for cost. Okay, it's always good to talk about cost, security. These are bonus uh, point if you can talk about, if you have time to talk about them. We can downsample raw data to lower the storage cost. For example, 10 lines of log can be turned, to one line. It means that we are losing resolution here, right? Resolution and precision of log data, but it might not be like a bottleneck. We in order to save cost, we can do that. Move. Then the other thing is that a consideration for saving costs is move old raw and recommended data to an archive cheaper storage after retention time. Recommendation algorithms. Then here it's a little more ML topic, but it's good to know. Recommendation algorithms are mostly two types: item-based collaboration, user-based behavioral collaboration. Item-based collaboration, it means the algorithm finds similarity between products, items, movies, and then if user A purchased first item, system recommends the second item to them because item A and item B are similar. However, in user-based behavioral collaboration, we find similarities between users based on their previous interests and activities and purchase history. And then if user A buys something, we recommend the same item to the user B, which is similar to user A. You got the difference, right? One is based on similarity between items and products. One is similarity between users and their past behavior. Then user activities are such as likes, dislike, comment, purchase view. Else, then each activity has a weight when it comes to calculate similarities and interest. Okay, this is important. Each activity has a weight. For example, comment has a bigger weight rather than like or dislike. And purchase is the most. It should be the most influential activity in compared to others. So when we create a similarity score, we should consider all those weights in our algorithm. Also, activity time is important. The most recent activities, are more important. It should give a weight to that activity. For example, if a purchase has been done, I don't know, 10 years ago, versus like a comment has been made 2 days ago, the second activity should affect the similarity score more and have higher effect on the score. Data model, what is data model? Data model, we want to keep activity log, user ID, product ID, timestamp, activity like, dislike, view, comment, rating. These are activity logs, right? Raw data, user ID, product ID, or for example, movie ID, timestamp, what activity is being done on this product. Is it a like, dislike, and then what is the comment, what is the rating? And the other thing is that at the end we want to store recommendation is like user ID and a list of recommendation. A list of recommendation means a list of product IDs. Okay. And then once we have product IDs, when they want to see detail, we can fetch it from cache, from memory, from database. And this list needs to be sorted by time, from the latest to the oldest, and also with popularity. Popularity means similarity. Okay. So we will have, for each user, we will have a list of product IDs, which is sorted by similarity score, the highest first, and the timing, the most recent first. And the other thing, okay, I think this system is not responsible to keep the specifications of product, video, these are not actually part of recommendation, but we need to mention as we are recommending them. Yeah, this is all I have for this system design. Again, the focus of this system design for on engineering side, not ML side. For ML side, please refer to other system design, ML system design. In future, we might have more system design in ML domain and ML ops, ML engineering, AI agents, and all that. But for now, I think this was a good set of information to share about a recommendation system. Thank you all for taking time, and hope you have a great rest of day or night, and take care. Bye bye.